Hi everyone, I'm Akshita Gupta, and today I'm excited to talk about efficient caching in Python. From everything from simple local techniques to more advanced external solutions. This is the QR code to the slide deck. You can scan it and follow along on your own devices if required. This might be helpful for people on the back. Meanwhile, a little bit about me. I'm currently working as a software engineer at Salesforce in the mobile app messaging team. And before this, I completed my master's in computer science from the University of Southern California. So today, we'll first set the stage by discussing what caching is, why it matters, and the goal of this session. Then we'll follow caching through different layers of a full stack system and discover how widespread and versatile it really is. We'll dive into Python's built-in tools for internal caching with some real examples. We'll see where internal caching falls short and where external tools such as Redis step in. All through the presentation, we'll discuss important concepts, discuss approaches, and strategies. Finally, we'll recap and open the session for questions. So, the topic at hand. Why do we want to talk about caching? Because just imagine, you walk into your favorite coffee shop in the morning. The barista already knows your name, your order, and even starts preparing it as you walk in. Wow, what a start. Till the barista doesn't change, you don't have to start from zero every time. That's the difference caching can make. It's like giving your system a temporary memory and establishing trust in the data we have already seen. And honestly, if you're a developer, you cannot escape caching. It's everywhere. In your web servers, your Python code, your databases, even your browser is caching as we speak. So we got an idea of what caching is. It's the process of storing data in a temporary location so that it can be accessed faster the next time it's needed. Simply put, it's about keeping things closer to where we need them, especially if we are going to use them again soon. A cache, however, is a software or a hardware component embedded somewhere in the system architecture. Even though caches are typically volatile storage, when used correctly, they help us reuse previously computed or previously seen data, massively improving the performance of our applications. So the goal of this talk is to understand why caching matters and how we can do it well in Python. Now, caching is super common. Right from the front end to the back end, we can cache several things in several ways. Say we want to fetch our shopping cart from this e-commerce website, shopnow.com. But even before we open the browser, our caching journey has begun. In our computer hardware, right inside or super close to our CPU are three levels of cache memory. L1 cache, the smallest and the fastest, with each CPU core having its own. L2 cache, slightly larger and slightly slower. Then L3 cache, shared across cores, larger than L2, but still faster than the RAM. These caches help us reuse recently used data and instructions, helping our CPU avoid slower trips to the RAM. Now, there are other forms of caching in the computer architecture as well. But the point is, caching began even before we opened our browser. Now say we have typed in the URL and hit enter. To access the website, our browser checks if it already has some parts of it cached locally, probably from a previous visit to the web page, like its HTML, CSS, JavaScript, and if the content is still valid, that's a cache hit, and the browser can serve it immediately. However, if the content is not valid, there are three possible scenarios. First, we manually clear out the cache, just because we enjoy doing that. And second, the particular content is being accessed for the very first time. However, in the third scenario, the content is still in the cache, but it's expired. This happens because when the content was originally fetched, it came with certain headers, like cache control and expires. These headers tell the browser till when the data can be considered fresh. And once that time passes, the browser marks this data as stale. This process in caching is also known as cache invalidation, essentially telling the system, hey, this version is too old, go get a new one. Now let's assume we got this cache miss. Remember, we wanted our shopping cart from this website. Naturally, our browser will try to resolve the domain name into an IP address. But before going to the DNS server to do so, our system looks for the IP first in the DNS cache. If the mapping is already cached, it's a cache hit, we got the IP. Otherwise, it goes to the DNS server, retrieves the result, and caches it for next time. Now that the IP address is resolved, our browser wants to query the application server. But more likely, the IP is of a content delivery network. A content delivery network, or a CDN, is a globally distributed network of servers that caches static content, like images, HTML, JavaScript, closer to the users, significantly reducing load times. At times, such caches also prefetch or preload content into the cache before it's even requested by the users. This technique, called cache warming, in which we essentially warm up the cache. Now it helps us reduce latency and improve user experience, especially during traffic spikes. But we are not in pursuit of just the static content. We want to log into the site and get our cart. So that means we are requesting dynamic content as well. We go through the CDN and the load balancer to reach the application servers. Inside each application server, there is some form of local, in-memory, or as we say, internal caching in place. These caches cache results of heavy computations, query responses, etc. And each application instance will have its own local cache. We'll shortly get to this in more detail. Right now, we need to fetch our cart. The server has to query the backend systems. Now, such large systems often have a separate caching layer before the database is reached. This could be a fast, distributed cache like Redis or Memcached. Basically, an external cache that sits between the application and the database. This could store frequently queried info, user sessions, etc. Anything that helps reduce the pressure on the database. Hold on to this thought as well. We'll get to this kind of caching in detail again very soon. But let's say we again miss the cache. The request hits the database. Now, even the database has its own caching tricks to speed things up. And finally, we find our content. During our journey, the relevant data was cached wherever necessary. Next time, we would get cache hits pretty early in the system. So what did we gain out of this discussion so far? We saw that at every layer, a cache's job is the same: avoid redundant work, serve things faster, reduce system load. Depending upon the system requirements, different caches are implemented and used differently. Some are external, some are internal, some are storing query responses, some are storing user sessions, and so on. We also learned about a cache hit versus a cache miss, and we discussed what's cache warming. And finally, we discussed what is cache invalidation, which is the process of removing or updating data when it's no longer valid. As the saying goes, there are only two hard things in computer science: cache invalidation and naming things. Cache invalidation is notoriously tricky. You invalidate too soon, and you lose the benefit of caching. You invalidate too late, and you risk serving outdated or incorrect data. There are a few common strategies for cache invalidation. First one being time to live, or a time-based expiry. As the name suggests, our cache data is invalidated after a certain amount of time. And then event-driven cache invalidation. These are triggered by changes to the underlying data. For example, when a value is updated in the database, its corresponding cache key will be invalidated. And finally, by now, we saw a lot of evidence that we can cache everything everywhere and anything anywhere. But should we? This is a very important question. Just because we can doesn't mean that we should. For one, caching is expensive. Most caches store data in memory, which is costly and limited. Caching unnecessarily increases infrastructure costs. Then more data equals more complexity in managing consistency. The more we cache, the more we have to invalidate or keep fresh. There will be a lookup overhead. Larger caches may increase this fetch overhead as they require more time to search through. Finally, it's like wasting resources. Caching entries that don't improve speed or are rarely used are simply a waste of resources. So, what to cache? While there's no one-size-fits-all solution, we need to rely on metrics, logging, even cache profiling, basically just understanding our data and seeing what data is accessed more often. If 80% of our traffic targets 20% of our data, we should only cache this 20% of data. This way, we can determine a cache size. And once we have a set cache size, even if the traffic patterns shift and begin targeting a different 20% of data, the overall volume of the data being accessed remains the same. In such a scenario, instead of increasing our cache size, we simply need to make room to accommodate this newly popular data. We do this by deleting or evicting less relevant entries. For this, we can decide on a cache eviction policy. You've probably heard of some of these policies, like first in, first out, FIFO, last in, first out, LIFO. However, the most popular one is least recently used, or LRU cache. This would be a time-based cache in which the entry that hasn't been used for the longest amount of time is removed first. Here's a thought. Let's imagine your fridge is your cache and it's full. You bring home groceries. How do you make space? By removing the oldest item? By removing the jar you put in last night? Or the pasta you haven't touched for weeks? Think about it. I really hope you don't eat that pasta. For now, let's be boring again and look into local internal in-memory caching. We will see how Python uses an LRU cache. Taking an example of the super simple function squareIt, it takes in an input and returns its square. The only catch, as we can see on line 4, the function sleeps for 2 seconds before doing so. We are calling this function with the input parameter as 100 and printing the returned square. Let's try and calculate the amount of time our function takes to execute. SquareIt still has the same function definition. However, on line 7, we took a note of the current time in the start time variable. Then we made our function call, and we measured our elapsed time. In this section, we are just repeating the function call to see what happens. In the output, we can see that both function runs took over 2 seconds. And we expected that because we are intentionally making our function sleep for 2 seconds. Now let's move forward and cacheify this. Python's functools module offers decorators, also known as wrapper functions, to help us cache easily. One such decorator is LRU cache. We import it and provide a max size to this cache. This is the maximum number of entries our cache can hold. And that's it. No more changes. We are still timing our function, and we are still calling it twice to see what happens. Pretty easy. And we can see in the result, our first execution took over 2 seconds as expected. But the second one took less than a millisecond. This means this in-memory cache memoized or remembered the computed result. Python didn't even call the function a second time. It just looked into the cache, got a hit, and we were good to go. This is super useful for computationally heavy deterministic function calls and when the input is repeatable. Now, functools also offers an alternative to LRU cache called cache. This decorator is essentially a shorthand for the LRU cache decorator, as the max size is set to none. It stores the results of all function calls without any size limit and doesn't evict anything. However, it's still an LRU cache internally. This implies if we keep everything else the same and run our code, the result will obviously be similar. The approach is great when memory usage isn't a big concern and when we want the previously computed results to always be available. Since both of these are in-memory caches, we know that the cache is cleared when the process ends, which is perfectly normal for this kind of caching. But what if we want our cache to stick around even after the script ends? For that, we can use the Python library called joblib. Unlike LRU cache, joblib caches results as files on the local disk so that the cache can survive even after our process ends. Just to clarify, this isn't an external or a distributed cache. It's still local to our machine because we are storing as a file and reading from it on reruns. So, using the tools we just discussed, it looks like we know how to cache internally. These are great when the input is small and repeatable, when we have a single server, or when our function does not depend upon external systems. But what happens when we scale up? If we have a system with multiple servers running the application independently, any local cache would be isolated to each of the application instances. This can lead to inconsistencies in data availability, unnecessary DB accesses. Let's look at the problem of unnecessary DB access. Say our application server wants to fetch the product details from the database for shopnow.com. This server might be doing something like this, where it is making a DB call to fetch the product details from the DB. And it caches the result on the server, obviously. But what if our app runs on multiple servers behind a load balancer? The first request hits the server 1, as we just saw, and gets cached in the memory of the server. The second request might go to server 2, which has no idea about server 1's cache. The result being, we hit the database again, even though another server already had the data. To solve this, we move from local caches to distributed caches, like Redis or memcached. As we discussed earlier, this would be an external cache which sits between the application and the database. All our application servers connect to these external caches over the network to read and write entries. And since they all share the same cache, it's distributed. Now, the terminology can be a little bit confusing. When we say in-memory, internal, local, we are typically referring to caches that live on the same instance as the application server. But Redis and memcached, being external, are still in memory because the data lives in the memory, but on their own dedicated servers, not on the application server. And because this data is still in memory, the access is extremely fast, typically within microseconds. Hence, this model gives us the best of both worlds, fast access speeds and consistent data across our system. We just discussed that these caches can be shared across application instances, unlike local caching. This also implies that our cache will persist even if the application server goes down or crashes. In terms of speed, distributed caches are also fast like local caches, but are obviously over a network. Hence, these are a popular choice for scalable architectures. Now let's look at a simple example of a Redis implementation and understand how it would work. We are creating a script which stimulates the fetching of data from a database. The function fetchUserFromDB goes to sleep for 2 seconds and returns a hard-coded JSON. So let's add some Redis to this now. We import the Redis module, and we first try to initialize our cache by connecting to the Redis server running on a specified port. Meanwhile, our fetchUserFromDB function remains the same. We add a getUser function, which first tries to read from the cache. As seen on line 18, it does a cache.get. If the data is found, it goes in the if block and returns from the cache itself. Otherwise, it executes the fetchUserFromDB function call to fetch the data from the DB. Then uses a cache.set function to save the result in Redis for later use and returns the user information. We make 2 calls and time the calls the way we always do and see expected results. In the first execution, we fetched from the database and cached our result. So the function call took over 2 seconds. Second time, however, it was a cache hit. Our function returned the result from the cache without further action. But we are central and distributed, right? Let's try rerunning our script from another client and see what happens. As we can see, running from a new client, it hit the cache both the times and gave us both the results in less than a second. After all this, some thoughts around the topic come to our mind. We know the pros of external caching by now, but are there any drawbacks to it? Well, yes, external caching comes with network latency, and this pursuit of making caches highly available and scalable adds complexity to our system. Are Redis and Memcached the only external solutions? Well, no. There are other in-memory distributed caches and other distributed caches that are not exclusively in-memory. For example, Apache Ignite. Out of Redis and Memcached, which is better? While both are excellent caches, the choice depends. We typically go with Redis if we want more than normal key value caching. It's more feature-rich and more flexible. Memcached, on the other hand, is more simpler, quick, ultra-lightweight, no-frills caching. So what did we learn today? We saw that when an app runs on multiple servers and we need a shared cache, we lean towards external caching. And like we discussed earlier, when we are caching small amounts of data or function results on a single server, we go for internal caching. What about when we want consistency plus ultra-fast local access? In that case, we go for a hybrid approach with both external and internal caching. Nice. Let's conclude our session. Whenever we think about cachifying our application, we should first think what data we want to cache. Our memory is limited. We should only cache frequently accessed data and the data that hardly changes. Then we need to choose wisely: internal, external, hybrid, how to evict, how to invalidate. The right strategy will make all the difference. However, when the data is highly dynamic, it is sensitive, like authorization tokens, or caching introduces a risk of inconsistency, we should skip caching to keep things safe and accurate. And once we take care of all this, we are not done and dusted. We need to monitor our cache hit and cache miss ratios to gauge effectiveness of our implementation. Caching is an invisible performance booster, but it needs to be done right to keep things scalable, responsive, and fast. And that's it.
Thank you very much.
Thank you so much for listening so patiently.
Okay, so if anybody has any questions, please line up at the microphone.
These are some topics for some further reading if you guys want to do, and let's connect.
So I have a question. I'm not sure I can form it very well, so I apologize if it's a bit vague. But in the early part of the talk, you were talking about the multiple caches happening kind of at every stage from the processor to like the data, all the way back to the database, within the database.
Yeah.
And it occurred to me, with all those layers of caches, it becomes very difficult to work out, like, to stop yourself from receiving stale data, basically, from one of the caches in that sort of stream of caches. I wondered if you had any recommendations for sort of avoiding returning stale data to the user.
Can you repeat the last part? With all of these hops, there's...
So it's like, so let's say your browser cache is one thing, but that might actually have been updated from cache data on the server, that might have been updated from cache data on the server, and so potentially, like, if your expiry's sort of out of sync, potentially you're caching out-of-date data that you've loaded from one of the many caches in your sort of application. And I thought that might be quite difficult to manage if you've got multiple caches. And if you're serving stale data, maybe that's quite hard to debug. I wondered if you had any recommendations for how you might avoid that.
So I think a lot of systems come into play here. It's kind of the responsibility of every cache that is in place to invalidate all through the system and kind of give that knowledge that, okay, this data has been updated, you know. And you know how we do a hard refresh at times on our browser when we feel like we're just getting the cached thing and we're not actually getting something that we have updated. So yeah, there's no recommendation as such. I just feel like whenever you implement your cache, you should cover all your bases, and you should have your systems in place that if something updates, everything in line can get to it. Yeah.
Okay. Thank you very much.
Yeah.
Do we have any further questions? Okay, if we could have another round of... Oh, no, we have a question. That was very quick. Very last minute.
Sorry. I have a question regarding caching instance methods, or the output of instance methods. If you use LRU cache, then you have the issue that you have circular references, which leads to memory leaks in the long term. And I was wondering if you have a solution for that. Like an idea how to solve this?
Memory leaks in LRU cache, that's a really good question. So I don't know how to solve it, but I think when we implement our LRU cache, then we should make sure that there are no memory leaks and that we are basically covering the whole thing. Yeah.
Okay. Thanks.
Okay, if we could have another big round of applause, please, for Akshita. Thank you very much.